Okay, so to solve this problem of controllability and observability, we use something called, we implement something called scan chains. And the idea is that if we could directly write to all the flip-flops, bypassing all the combination logic, we could control all combinational inputs. So in other words, if I could directly access, let's say I want to test this 3 gates here, the combination logic here. If I could directly write to these 4 flip-flops driving the inputs without having to go through all this previous logic, then I would have a similar case as, and I would have a similar situation as what you see here. Okay, here I'm able to directly write to the 4 input flip-flops. If I could do that even here, directly write to these 4 flip-flops, then I would effectively have controllability on the inputs. And similarly, if I could directly read this flip-flop, what its contents, what its value is, then I could have observability. Okay. And if I had that, then I would be able to test all this logic comprising these 5 flip-flops plus these 3 gates. All of that could be easily tested. All I need is controllability on the outputs of those 4 flip-flops and observability on the flip-flop that's at the XOR gate output. So to accomplish that, we use something called scan chains. And the idea is the following. We add a mux before every flip-flop. Okay, and that's what I'm showing here. So here's my original flip-flop, and the input to that flip-flop, I put a mux, 2 input mux. The mux select is a signal that I'm going to call shift enable, and you will see why later, but that's the name of that mux select, shift enable. Now, all flip-flops are connected. All flip-flops in the circuit are connected in an arbitrary sequence to each other in what we call a scan chain. And that connection is made through the mux. So this mux has 2 inputs. One of these inputs is the original functional input that was going to the D pin. Okay, that functional input now goes to one of the inputs of the mux. The other input of the mux is connected to some other flip-flop directly. Okay, and so every flip-flop is connected to another flip-flop through this mux input, and that chain of flip-flops connected through these muxes is what we call a scan chain. And when the scan enable is 0, when the shift enable is 0, so when SE is 0, the flip-flops receive the original functional input from the functional logic, from the combination logic. Okay, so this from functional logic means there's potentially some combination logic here that's sending that input. But when SE is 1, the flip-flops D pin gets its input from the scan chain, from the adjacent flop in the scan chain. So that's the idea here. And if I show the scan chain in its full context, then this is what it would look like. I have reproduced this circuit. This circuit I've reproduced here, with the exception that I've got those muxes in front of every front of every flip-flop. Okay. So the original circuit, which is, this original circuit is intact. Okay, the original circuit is intact here. The only thing I've added in order to enable testing is I've added these muxes at the inputs of every flip-flop. And then the flip-flops are connected in this scan chain through this, you can see the red line. The red line indicates the scan chain. So somewhere I need some input to the scan chain, I'm calling that scan in. So there's some way that I have to feed this scan chain with an input. That is a scan in input that you see on the left in red. And then the first flip-flop in the scan chain is the flip-flop I'm pointing to here. And then the scan chain goes, along this red line. So you can see the arrows. So totally there are 8 flip-flops in the scan chain. Okay, so the length of the scan chain in this case is 8 flip-flops. The flip-flops are connected sequentially in the scan chain. And this is what ends up happening when we introduce these muxes and create scan chains. So we have added some, we have sort of burdened the logic a little bit. We have added these muxes whose only purpose is to enable testing. They have no functional purpose. Okay. Now what happens? Now when I want to put some known values in any flip-flop, I simply have to shift those values into that flip-flop through the scan chain. So I run a clock, and every time a clock edge comes, the flip-flop captures the value from the previous flop in the scan chain. Okay. So let's take any example here. Let me annotate. So let's assume that the instance names of the flip-flops here is the flip-flop here is F1, and then there's F2, and then the flip-flop there is F3. Let's just imagine these are the instance names of the flip-flops. And then we have F4 here, F5, F6, and then there's flip-flop F7. So obviously in a real scan chain, in a real netlist, the flip-flops in the scan chain will not have this very sort of regular instance name. They'll be all random and arbitrary instance names, but just for the purposes of our understanding, let's say that these instance names are also reflecting their sequence in the scan chain. Again, that will never be the case in real life, but just now I'm naming them like that. And so if you look at the flip-flop F7, its predecessor or in the scan chain is F6, and it's and the next flip-flop in the scan chain after F7 is F8, okay, which you see on the right here. So every flip-flop has a if it's in the scan chain, will have a previous flop in the scan chain and the next flop in the scan chain, except there will be one flop. So in this case, F1 is the first flip-flop in the scan chain. Each input comes from some scanning input that I have to provide, and that we will see later how that comes. But for now, just imagine that I'm able to I have some for the scan chain, there is some scanning input that I control. And then there'll be the first flip-flop in the scan chain connected to that scanning input. Then the scan chain occurs after that. And the final flip-flop in the scan chain, in this case F8, is connected to an output called scan out. Okay. So this is how a scan chain is implemented. In real life, in real ASIC, the scan chain length will not be 8 flip-flops, it will be many hundreds of flip-flops, or even thousands of flip-flops. Okay, so scan chain lengths are hundreds to a few thousand. But for this example here, we have a scan chain length of 8 flip-flops. And what happens is that if I run a clock for 8 clock cycles and I feed values through scan in, okay, then I can feed 8 values in every clock cycle. I can feed a value at scan in, and that value will go through to F1. And in the next clock cycle, that value in F1 will go to F2. In the next clock cycle, the value in F2 will go to F3, and so on. So by the time I have 8 clock cycles, this entire scan chain of 8 flip-flops will be fully populated with known values. Okay, and all those 8 values would have been fed in through that scan-in input, through that single input. Okay, so this enables me to put over some multiple clock cycles. It enables me to put known values into every flip-flop in my circuit. And once I'm able to do that, then life becomes much easier to test the circuit. Because then once I have known values in all the flip-flops, then those flip-flops are driving data through the combination logic. I know what data to expect. I know what to expect as at the output of the combination logic based on the values I put into the input flip-flops. Okay, and then so I know I would know what value to expect at the output of the combination logic. That value will be captured by a flip-flop in the scan chain. Okay, and then I take those values out through scan out. Okay, so the way the scan testing works is that initially I shift values into scan chain. During the shift operation, the scan enable is set to 1, so that all the flip-flops are only capturing the data coming in through the scan chain, not the functional data coming through the combination logic. Okay. So first I populate the scan chain by setting the shift enable signal to be 1. Then once the scan chain is fully populated, I change the shift enables value to from 1 to 0. When shift enable is 0, then the flip-flop will capture the outputs of the combination logic. Okay. So in this case, first I run 8 clock cycles to fully populate the scan chain. Then I run one 9th clock cycle where the shift enable has changed to 0. And now in that 9th clock cycle, all the flip-flops, instead of receiving data through the scan chain, will receive the data through the combination logic. That combination logic is processing the data that was shifted in during the shift cycle. And then that 9th clock cycle is what I call a capture cycle. And during the capture cycle, the flip-flops are capturing the values from the combination logic. Once that capture cycle is complete, all the flip-flops values have been changed. Whatever I had shifted into them, that value would have changed because the flip-flops would have captured the output of the combination logic. So then I again start shifting. So I start my 8 shift cycle. My 8 clock cycles were shifting the next pattern through scan-in. But while I'm shifting that new pattern, the output of the old pattern is getting scanned out through scan-out. And I can just observe scan-out for 8 cycles and see if the outputs coming out are what were expected. And if all the outputs were expected, then I know the circuit is defect-free. If any output during those 8 cycles is not what is expected, then I know there's a defect somewhere in the circuit, and I can either discard the chip or find a way to do a workaround. Okay, or easily I'll just discard the chip. So that's the way scan works. Now, as I said earlier, the length of scan chains in typical A6 is several hundred flip-flops. Now, now A6 will have maybe 1 million flip-flops. You could have one single scan chain of length million, but that would be very inefficient because you would have to run 1 million clock cycles just to populate the scan chain. So we don't like that. It'll take a lot of time on the tester, and then the test cost will become very high. So instead of having a single scan chain of million flip-flop length, what we do is we would make multiple scan chains. Let's say each scan chain is only 1,000 flip-flops long. So you would have maybe 1,000. You would have 1,000 scan chains in the ASIC, and all those 1,000 scan chains would get populated in parallel during 1,000 clock cycles. So in general, ASICs have many scan chains, not just one, and this enables us to populate all the flip-flops much sooner because you can be populating all the scan chains in parallel. The number of clock cycles during the shift operation is equal to the maximum length of any scan chain on the ASIC. And we want to minimize the time on the tester. So we want to minimize the number of clock cycles during shift. So it is important that the max scan chain length is not too much. And so ideally, if all chains have equal length, then the maximum chain length will be minimum. Okay. This is called scan chain balancing. So we try to, when the scan chains are implemented in an ASIC, it is done in a way that it is balanced as much as possible. So all scan chains will have somewhat equal length. If you had a very short scan chain, let's say if all the scan chains were 1,000 flops long and one scan chain was only 100 flops long, then that short scan chain will be fully populated after 100 clock cycles. And then while the other scan chains are being populated for 900 clock cycles, that short scan chain will just remain idle, okay? Which is fine, no problem, except that it's sort of a bit of a waste of, it's a bit of a waste in terms of resources. It would have been better to reduce the total scan chain length and make every scan chain equally long. So that is called scan chain balancing. The order of flip-flops in the scan chain does not matter for testing the ASIC. The order of flip-flops in the scan chain can be arbitrary. You just need to know what that order is, so that you can populate the right value during the shift operation. But otherwise, what that order is of absolutely no importance. Now, since scan chains are very common, in fact, pretty much you would never design a chip that is not testable. And to enable testability, you have to have scan chains. At least to test the standard cell logic, you have to have scan chains. So since scan chains are very common, in fact, that I would consider them ubiquitous, standard cell libraries will usually have what I call scan flip-flops. These are flip-flops which combine that mux and D flip-flop in a single cell. So instead of having a separate mux standard cell followed by a D flip-flop standard cell, since this pairing is very common, standard cell libraries will almost always provide what is called a scan flip-flop, where this mux and DFF are combined into a single standard cell. Okay, and we simply move the D pin of the flip-flop. We just show it as a D pin of the mux. The mux input is called D. In other words, this is the functional input to the flip-flop, the D pin. And then the scan input will have some name. I'm calling it SIR for scan input. Okay, so those are the two inputs. Those are two sort of those are two inputs to a SDFF. And then you also have the third input, which is the shift enable input. So any SDFF, a scan DFF, will have three inputs, whereas a DFF, an ordinary DFF, will have only one input. And I'm not counting the clock here. Okay, so so this is a very common standard cell, and it has a Q output and the clock. So if you look at your standard cell library, you will see DFFs, but you will also, for every DFF, you will likely see a corresponding SDFF, where the SDFF is nothing but the mux and the flip-flop combined. And this combination is not done by simply taking the mux standard cell and the DFF standard cell and just somehow combining them into a single standard cell. Instead, this will be designed from scratch, from ground up, and will be optimized so that if you were to look at a mux standard cell area and a DFF standard cell area and add them, that area you should expect it to be much less than the area of an SDFF that implements the same function. So this combination is optimized in some fashion in terms of area and delays, and then these cells are in the library. So when you do synthesis, you would have to tell the synthesis tool whether or not to use SDFFs or not, and the dot lib will indicate which input pin of the SDFF is the scan input and which input is the functional input. And so I would encourage you to kind of look for the SDFFs in the dot lib and convince yourself that you can tell which is the scan input, which is the shift enable, and which is the functional input. And then we will do some exercises as part of your assignment where you will synthesize with SDFFs and without SDFFs, and then find out what the implications are of doing scan, because the SDFF area will obviously be larger than the corresponding DFF area, and that's an area overhead we unfortunately have to bear in order to make the chip testable. So one of the impact of making a chip testable is that the chip area increases in order to accommodate all the logic we add for testability, and that's an unfortunate but unavoidable overhead. Also, the timing of the timing properties of these SDFFs may be worse than of DFFs. So we will talk about setup and hold time at some point in the future. But for those of you who know what setup time is, the SDFF setup will usually be larger than the DFF setup, and that will obviously impact the performance of the chip. So there is some cost that is borne by doing scan chains, but it's not something we can avoid because testability is not testing is not an option. You have to test a chip before you sell the chip, and so this is an overhead that we will explore in one of your homework assignments.